When you throw on a science podcast like this one that you're listening to right now, you may not know much about the topic you're about to hear about, but you probably expect at least one thing. You expect that whatever we're going to tell you is going to be true, or at least will be a theory with a great possibility of being true. Not today, though. Today on our show, we're talking about a theory of the universe that we already know is completely wrong.
You might ask, why would we do such a thing? Why would we dare waste the next 20 or 30 minutes of your life talking about something that we know is false? But I'm going to argue that sometimes even wrong theories are really important, maybe not in advancing what we know about the universe, but helping us understand ourselves and what the science was like at a point in time. So with that in mind, we're going to talk about this paper from 1931, which, as far as I'm aware of, is the very first paper in history where somebody tried to put forth a scientific explanation for the beginning of the universe. I think that's a pretty big deal and a really exciting landmark intellectually, even if it turns out to not really be true.
And I think it's just kind of revealing. It's hard to imagine now when you grow up kind of knowing, like hearing about the Big Bang and everything like that, what it would be like to really start fresh and just from your experience living as a human on Earth, what you would have imagined the universe would have started as. Also, before we get started, apologies if you hear some background noise or static coming from Dan's mic. We've been having some technical difficulties, but thanks for understanding.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and a regular consumer of Wondrium's content for the past 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and even science. For me, it's like taking an intro-level university course from a great professor on a subject you've always wanted to know more about, but without the big tuition fee, and all in the comfort of your own home or daily commute. Recently, I've started to listen to a series of lectures on Wondrium on the topic of Norse mythology. Over 24 lectures, this course explores how the people of the Norse culture view things like fate, as well as their place and significance in their world. Along with these more heavy questions, these lectures also contain a lot of fun stories about things like gods, dwarves, spells, and berserkers. It was a blast to listen to. So if you want to learn more about Norse mythology, or really just about anything else, you should give Wondrium a try. You can sign up for Wondrium now through our special URL to get a free month of unlimited access. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. All right, so let's start by painting a picture. It's May of 1931. So Einstein's theory of general relativity had been around for about 15 years now. And over the last decade or so, the foundations of this new science of quantum physics had kind of come into place. People figured that stuff out, still dotting the I's and crossing the T's, but most of it was there.
It's interesting that quantum mechanics being such a weird theory, that even came before thinking about the beginning of the universe.
Yeah, that's right. Another thing that had just been going on was the first, measurements that I would call empirical or observational cosmology. So in 1929, it was when Edwin Hubble and Milton Humason reported the first observation showing that our universe was expanding. The space of our universe is getting bigger, as time goes on. So this was a pretty exciting time to be a physicist, right? You've got a pretty new theory in Einstein's relativity. You have a very new set of ideas in quantum physics. You have these new observations about the universe evolving and changing. There was something in the water then. It was a very exciting time to be figuring out or contemplating our universe. So now imagine you're picking up the May 9th, 1931 issue of the journal Nature, like flipping through the pages. This journal like covered all sorts of scientific topics. So you'd find a bunch of different articles on chemistry. There was one article in this particular issue on forestry research. There was one about the electrical properties of the atmosphere. And there was even one that I found in this particular issue that was about the insect remains found inside the gut of a cobra. So that one seemed pretty exotic to me. But alongside all these various scientific ideas and, things people had noticed, there was this really important, very, very short paper by this Belgian astronomer and mathematician named Georges Lamartra. So when I say short, I really, really mean short. The whole thing, I counted it, it was 457 words. So it's like 4 paragraphs.
You counted the words?
Yeah, I was really curious.
Or did you use a little word count?
No, I have this thing is a scan of a 1931 paper, so it's not digital.
Oh, wow. You went and counted 1, 2, 3, 4?
Yeah.
Oh,
That's
wow.
the only way I had to do it. If I miscounted, I apologize, but by my count, it's 457 words.
How long did that take?
Not long. 457 isn't that big of a number. You can get through it pretty quick. So, okay. The title of this article is one of my favorites in the history of science. It's just simply, quote, "The beginning of the world from the point of view of quantum theory." This is next to some article about insects in a cobra gut and forestry research. It just way out in left field.
It sticks out.
Yeah, for sure. Before we actually get into what's the contents of the article are, let's say a little bit about Lamartra himself. So he was about 37 at that time, and he had been a professor in Belgium at the Catholic University of Louvain for about 6 years. He had a lot of talents as a scientist, but he was probably most famous for his work on general relativity. In particular, he was like one of the really important pioneers in figuring out what general relativity implied about the universe as a whole. So trying to do the earliest steps of cosmology using Einstein's theory.
And we do really mean the earliest steps of cosmology. At this point in history, we didn't even know whether the Milky Way was the entire universe. Cosmology was in an infant stage as a field of science and really didn't have the foundations that it does today.
So, like other really new fields of science, there were not many people working on this area at the time. Lamartra was just one of a few scientists who were thinking about questions that we now call cosmology. And not only was he one of a few, but he was also, like, of that few, he was the one who consistently got the right answer when he thought about these questions. So, like, a lot of his colleagues, like including Einstein, looked at the equations of general relativity and applied them to cosmology and got the wrong answer sometimes. Lamartra really, like, along with, I would say, Friedman, were two figures at this time who had really figured out a lot of this stuff correctly before the rest of the community kind of caught up.
So now we have this context about Lamartra, a brilliant cosmologist in an age when cosmology was hardly a science. So now let's dive into what this 1931 paper really had to say about the quote-unquote beginning of the world from the point of view of quantum theory. Big title to live up to.
It opens with a shot across the bow. I like papers that do this. So the very first sentence is a quote from the famous English astronomer Arthur Eddington. And it reads, quote, "Philosophically, the notion of a beginning to the present order of nature is repugnant." In other words, like Eddington, who's kind of speaking on behalf of the whole scientific establishment here, is telling us that scientists aren't even supposed to think about how the universe began. To him, it's just not a scientific question. It's off limits. It's kind of gross to even talk about.
Do you think that came we could speculate about what that came from, but do you think in part it was like a rejection of religion, and in a way like the beginning of time was a very religious notion?
I think that probably had something to do with it. Like, there had just been a lot of wide-eyed speculation about it by theologians and others for as long as human beings have existed. And that sort of like unguided speculation isn't something scientists do. We can speculate, but we speculate based on logic, reason, and observations. And I'm sure it just seemed like a topic that you couldn't make progress in addressing using the scientific method. Now, we have made progress, but I'm sure in 1931 that seemed very unlikely.
I wonder if we have any of those things today that people, I honestly, maybe like foundations of quantum mechanics or something like that people consider, purely a philosophical issue. Like, you don't need it to like, shut up and calculate kind of people.
Yeah, I think that's a great example. And like others that are maybe a little more down to earth, or I guess that's a bad choice of words, but like if I want to talk about whether we've seen aliens or something, or extraterrestrial, like, that's something most scientists like, I don't know, like that doesn't seem like the sort of thing we should be talking about now. And to be honest, on the other hand, most people who are talking about that stuff in a UFO context are not thinking very scientifically. But maybe that was the same feeling Eddington had about the beginning of the universe in 1931.
Right, when Lamartra was quoting this Eddington quote, did he respond to it, or was it just like a cheeky thing to put in the beginning?
I think what he was trying to do is to look face on, saying, I know if you're reading this, you probably think this isn't something I should legitimately talk about. And, you think that I'm not being scientific by doing it. I'm aware of that, is what I think he's telling you, and I'm going to do it anyway.
Yeah.
So Lamartra then begins to lay out his argument for how one might be able to infer how our universe began using scientific principles or arguments or reasoning. He starts by invoking the first and second laws of thermodynamics. So the first law of thermodynamics is basically just saying that energy is conserved. Okay, so you don't create or destroy energy. And then the second law of thermodynamics says that as time goes forward, the amount of entropy tends to increase. We've talked about entropy before on this podcast in a bunch of different cases. But I think if you combine these two laws, what really matters to Lamartra is that as the universe expands and in time it advances, you'll have the same amount of total energy, but you'll tend to have a larger number of total particles. So maybe, for example, he's picturing big atoms kind of falling apart into smaller atoms as time goes on. So you have the same total amount of energy, but in more, as he would say, quanta, or more pieces of particles, more pieces of matter as time goes on.
Wait, so what's the logic behind this? He's saying that particles are going to like decay and stuff?
Yeah, so I think that's what he had in mind, something like that. So we didn't know that much about atomic physics at the time. So, the neutron hadn't even been discovered yet. So we're using pretty elementary ideas of what this would look like. But yeah, it's what the second law of thermodynamics really says has to happen. So, and it's what modern physicists think would happen too. If I took a bunch of, Higgs bosons or something, and just put them in a box and waited to see what would happen, they would decay very quickly, and you wouldn't find new Higgs bosons being created. You just find these particles decaying into the lightest things they can. And because energy is conserved, that means there'll be many more particles when you're done than when you start. So I think, from the principles of thermodynamics, something like Lamartra's logic follows. Although with a lot of open questions that he couldn't have possibly had answers to at the time. I'm going to use some modern numbers in Lamartra's context here, but like there are about 10 to the 80 atoms in the observable universe today. He didn't know that, but that's about right. So, you might imagine that if you could go back in time, you'd reach a point where there were only 10 to the 79 atoms. But those atoms on average were 10 times as massive. Okay, so maybe instead of a lot of hydrogen and stuff, there were things like oxygen or boron or something making up most of the mass of the universe. And then maybe if you went back way farther, you'd find there were only 10 to the 70 atoms instead of 10 to the 80. But the average atoms were, tens of billions of nucleons in mass or something. That's the sort of thing he was picturing. And now if we take this to the extreme limit, the infinite limit, you might find yourself at a point in time, a very long time ago, where all of the matter in the universe was all glued together into one giant single solitary particle. Lamartra called this particle the primeval atom, and he imagined that might have been the state that our universe began with.
So it's quite a bit of extrapolation from us knowing that from the second law of physics, maybe we'll have particles decay, we'll have more particles, to then look backwards and be like, oh, they must have all come from one single atom. It's like a funny thing to think.
Yeah, that's right. And like, if you take a modern particle physics class, you don't walk away thinking this makes sense. We don't think that, atoms can be infinitely large, whatever, but think about it from a 1931 perspective. Like, we've kind of fleshed out the periodic table. It just keeps going higher, and we don't know about things like, neutrons and the structure of the atom yet. All we know are there seem to be nuclei, and there are electrons around them, and there are bigger and bigger and bigger nuclei. And the bigger they are, the more likely they are to tend to decay. So maybe that just goes on without limit. And maybe, if you went back far enough in time, you'd find these really exotic, super, super massive atoms or other forms of matter, who knows, that could constitute Lamartra's primeval atom.
It's not the most modern picture of the universe, but maybe you could imagine how this idea of a primeval atom would have made sense given the physics of the day. But it still leaves a lot of open questions, like why would there only be one primeval atom? And where would this atom come from to begin with?
Let's talk about a universe with just this one primeval atom and what that would be like, okay, what that would represent, because I think where your mind is going is exactly where Lamartra goes in his next paragraph. He invokes what had been recently learned in the years ahead about quantum physics to talk about what this universe with one solitary primeval atom in it would be like. And he invokes a Heisenberg uncertainty principle. He says, according to quantum physics, you fundamentally cannot predict when something's going to happen. So if I take some atom, some real world atom, and I ask, when is this going to decay? I can tell you what its half-life is. I can tell you the probability that it will decay at a given time or whatever, but I can't tell you when it will decay. It's a random process. It's fundamentally random. So this primeval atom might sit there for a while, who knows how long, but it will eventually decay. But before it decays, there will be a fundamentally uncertain length of time that it had existed first. Okay, so you can't know when it happens. Here's where Lamartra's argument gets a little philosophical, and I think pretty interesting. So I'm picturing this universe. I've got one single primeval atom sitting in it. In such a universe, we can ask ourselves, what would it mean for us to use a word like space or time? Whenever we measure a quantity in connection with space, we're measuring a distance between two different things in space. But there aren't two things in Lamartra's universe with one primeval atom. So I can't measure any distances, and I can't measure any speeds or anything because I don't have anything to compare the location of the primeval atom to. So I can't talk about space. Really, space, for all intents and purposes, does not exist yet. And then let's talk about time. Whenever we make a measurement in connection to time, what we're really measuring always comes down to an amount of time that passes between two or more different events. But nothing has happened prior to the decay of the primeval atom. So I can't measure any events or the durations between events. So for all intents and purposes, there is no time either. So I'm going to quote Lamartra here. Quote, "If the world had begun with a single quantum, the notions of space and time would altogether fail to have any meaning at the beginning. They would only begin to have sensible meaning when the original quantum had been divided into a sufficient number of quanta." In other words, space and time to Lamartra only come into existence when quantum physics randomly causes the primeval atom to decay. This event, this decay of the primeval atom, represents the beginning of both space and time, and thus the beginning of the universe itself.
Yeah, I mean, I feel like this is the part of the logic that is kind of most compelling, right? Because if you were to just ask, how does space and time emerge from nothing, like you imagine that it has to emerge from like one thing and then expanding from there. So in that way, it feels kind of like well motivated in this sort of core philosophical way.
Yeah, I agree. And at least it makes me, I don't know about you or other people, but it makes me think about things I've read about emergent gravity or emergent space-time. Like maybe space-time aren't fundamental things, but once you have different things that you're comparing to one another, either in terms of how, much they interact with each other, which is kind of a measure of space, or maybe in their causal properties, which is related to time, we start to have convenient notions of space and time emerge. But maybe they wouldn't exist under all circumstances, kind of like in the solitary primeval atom circumstance. Maybe, space and time are something that only exist when there are these convenient notions that we need to account for them with. Let's take a step back and assess this paper of Lamartra's and its ideas from a more modern perspective. First of all, let's just be clear. There's no reason to think that there was ever a single primeval atom. And as far as we can tell, space and time did not come into existence in the way that Lamartra originally imagined or wrote about in this 1931 paper. There very well may have been a space-time singularity at the moment of the Big Bang or something, but all of those things would be worked out by general relativity practitioners or experts in the 1960s, like long 3 decades after this. So Lamartra didn't have any notion of any of that. That's not what he was talking about. Contrary to Lamartra's idea or vision of the early universe, a modern cosmologist pictures your early universe is packed full of particles, tons and tons of particles in a tiny little volume of space. Maybe Lamartra thought the universe after the decay of the primeval atom looked that way until it expanded out. I'm not sure, but it's a very different picture than what Lamartra was writing about in 1931.
So congrats, you've now spent 20 minutes learning about a theory of the universe that is patently false. But I hope you don't feel like your time has been wasted, because we think there's still a lot of value to be gleaned from an important historical paper like this one, even if it does turn out to be wrong.
An analogy I like to draw is between Lamartra's work and the work of the biologist Jean-Baptiste Lamarck. So Lamarck was a predecessor to Darwin. He worked out a theory of evolution where organisms could pass on the traits that they acquired during their lives to their offspring. So maybe some organism has good reason to use their muscles a lot and they get stronger, and then their children have stronger muscles. That's not how real biological evolution works. That's not what, Darwin's mechanism through natural selection is very different. But Lamarck's ideas were kind of the first scientific theory of evolution. So I would argue that if you really want to understand the intellectual tradition or scientific tradition of humankind, you shouldn't just study Darwin, you should study Lamarck too. And if you want to understand the intellectual tradition and progress, scientific progress of humankind when it comes to our understanding of our universe in its beginning, you wouldn't just want to understand the Big Bang theory as we currently understand it, but also ideas that came before it. And in particular, George Lamartra's primeval atom theory.
Thank you for listening to our show. If you like our show and you want to support us more directly than just being a listener, which we already appreciate, you can find us on Patreon and support us there. For as little as $3 a month, you get access to ad-free versions of the episodes and the opportunity to ask us questions and listen to monthly Ask Us Anything episodes only for our Patreon subscribers. So you can find that at patreon.com/whythisuniverse. This episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. He's also the author of many books, including, most recently, At the Edge of Time, exploring the mysteries of our universe's first seconds. So if you want to hear more about the true theories of cosmology, or at least the ones that we believe the most now, then definitely check out his book. All music in this episode was produced by Jake Kleinbaum. Why This Universe is part of the University of Chicago Podcast Network.